Hello, everyone. My name is Michael Okonkwo, and today I will be going over my semester-long data mining project for Professor Pablo Rivas. And with that, it is detecting illicit material. And to be specific, it's in regards to stolen car parts on client-to-client market spaces such as Craigslist and OfferUp. So to start, we'll go over the agenda for today. And to start off, I'll give some background context regarding the project, the methodology behind why I did what I did for the project, and as well as the results and conclusion and further implications for this project. So to start off with some context. As technology and the internet becomes more integrated with societal function, our lives become much more efficient in daily tasks such as communication, of information and cooperation for activities such as buying and selling goods. Unfortunately, this comes at a trade-off, which is a concerning increase in cybercrime in client-to-client market spaces such as Craigslist, OfferUp, or Etsy, such as scamming, forced theft, sexual misconduct, and other violent crimes. And there are discussions with new technology today that we could leverage large language models, computer vision models, and multimodal models to find a diverse set of high dimensional spaces within client to client marketplace data that is theorized to facilitate the discovery of patterns and lead to findings that could detect crimes such as the list mentioned before, which is theft, scamming, sexual misconduct, or other violent crimes. And so, to be more specific, I'll go over my project outline. And this project will attempt to utilize computer vision models as a feature in identifying patterns related to potential stolen car parts within Craigslist. And the following present key details in bringing this goal into fruition. First of all, I will be in charge of collecting and pre-processing valid visual data from Craigslist postings. Then I will be in charge of embedding the visual data that was collected into high dimensional vector spaces of numerical data using visual transformers or VITs, as well as the normalization of high dimensional vector spaces into a variety of lower dimensions and evaluating these lower dimensions to find the optimal level of dimensionality reduction. And then we will move on to the reduction of embedded vector spaces to two dimensions for visualization and the use of KNN on the optimal lower dimension space to analyze centroid descriptions along with the nearest neighbor images to the centroid and discuss project implications from this. So to start off with the project and the methodology, um, data and pre-processing. The data set obtained for research consisted of visual data, lots of visual data of various car parts within Craigslist postings. And that could mean trunks, the interior, exterior, anything you can really think of in various amounts of angles and, of course, various amounts of people. And of course, this means it's a very large data set and was very unorganized as it wasn't tailored to anything specific besides the fact that it had car detailings. And with this, to store such a large data set, we utilized tar files, compressed the Craigslist listings, and this allowed for storage in batches. And in regards to pre-processing, duplicate visual data was filtered out, as well as missing image data or invalid image formatting. So onto image embedding. And with that, the next step involved transforming the visual data that was collected in the .tar files to a more applicable format for our machine learning model. And to be more specific, the images would be transformed into a high dimensional vector space, which consisted of numerical data corresponding to the features of pixels within the visual data. So, of course, each pixel will correspond to a specific number, and then that's how we would transform that data. And we will be using the Dino V2 visual transformer or VIT for this. And details include, of course, it's a computer vision model, which means it regards transforming visual data specifically. And a huge advantage of this, using this specific model, which is Dino V2, is that it's very scalable, as V2 allows for the processing of images in batches, which makes data transformation much more efficient for large data sets, such as the ones that we're using for this project today. So to go on to dimensionality reduction, following the embedding of our visual data into high-dimensional vector spaces, we also have to consider normalizing our data to improve our performance and accuracy. There are two forms of dimensionality reduction considered, which is principal component analysis, otherwise known as PCA, or uniform manifold approximation and projection, otherwise known as UMAP. So for PCA, it's known as a mathematical procedure to transform potentially correlated data into its principal components, which is otherwise known as the lower dimension version of the data set. And with UMAP, this is something that would turn its high dimensional graph representation to lower dimension graph representation. And this might seem very similar to PCA, but one thing that makes UMAP distinct is that it's optimized for visualization because it maintains a similar structure through transformation due to its ability to capture local relationships within its clusters, as well as global relationships between, of course, distinct clusters. So on to clustering, grading, and visualization. To start off, of course, we use k-means for clustering, and this was performed after PCA reduction to our various dimensions. In this specific project, we're going to go to 16, 32, 64, and 128 dimensions, respectively. And to find the optimal dimension to reduce to, we graded the clusters based off of three different scores, which was the reduced silhouette score, the reduced Kolinsky-Harabask index, and the reduced Davies-Bouldin index. So to start off, the reduced silhouette score would measure how similar an object in its own cluster is compared to other clusters, while a reduced Kolinsky-Harabask index would evaluate the variance ratio between intercluster data, which is data between different clusters, versus intra-cluster data points. And last but not least, the reduced Davies-Bouldin index would measure the average similarity between each cluster and its most similar cluster. And this would be distinct because the lower the score, the better, because it indicates a better separation between these clusters. And last but not least, of course, visualization. And with this is where UMAP comes into play. As you can see here, this is an example of how UMAP would be utilized to just show how k-means clustering would look like. Of course, each cluster is assigned a different color here. And on to KNN. KNN in this case would be used to identify centroids and basic information such as post ID and caption of visual data. And of course, KNN identifies a specified amount of neighbors nearest to each centroid. So each data point is related to a specific image. So instead of analyzing numerical data, this specifically will have a centroid and a variety of closest neighbors. And you'll be able to examine visual data such as a centroid of tires or trunks. So on to our results. This is the result from the reduction using PCA to 16 dimensions. And of course, here, as you can see, the reduced silhouette score is 0.0539. The reduced Kolinsky index is 1526.86, and the reduced Davies-Bouldin index is 3.588. So onto the 32-dimension clustering, the reduced silhouette score was 0.056. The reduced Kolinsky index was 1528.65, and the reduced Davies-Bouldin index was 3.582. For 64 dimension, the silhouette score was 0.057. The reduced Kolinsky-Harabask index was 1539.83, and the reduced Davies-Bouldin index was 3.409. And last but not least, the results from grading the 128 dimension clustering, the reduced silhouette score was 0.056. The reduced Kolinsky-Harabask index was 1544.15, and the reduced Davies-Bouldin index was 3.508. So on to results for KNN evaluation. I am not permitted to show you the actual results from the KNN evaluation as it reveals sensitive user information. However, it would look like an accumulation of similar car parts in each cluster. Just for example, there would be a centroid that would say a post ID and a brief description, maybe. And then let's say this centroid was more geared towards tires. You would see a bunch of different tires and a bunch of different angles, and as mentioned before, one cluster would present, of course, tires or trunks or just interior parts in different angles. And this is how it would kind of look like, in the sense that like it would specify specific parts, and this is all for that. And so onto our conclusion, some takeaways is that this project efficiently highlight the effective ability in leveraging AI as a feature that would aid law enforcement in detecting and interrupting unlawful practices in commerce. To specify the utilization of VITs as shown in the research expanded on an ability to detect potential illicit visual data which enhanced law enforcement and their ability to detect stolen car parts. And by automating analysis of large visual data sets, this product significantly improved efficiency in detecting illegal activity while reducing the chance for human error. And the broader impact of this project is that models such as the Dino V2 model highlighted can extend from just the scope of illicit transactions to detecting human trafficking in client-to-client marketplaces, as well as misconduct involving minors. Furthermore, this implication of provided for this product significantly enhances public safety and internet platform integrity in client-to-client market spaces, but just in the internet in general. Um, and by illustrating the transformative potential of AI-driven solutions for the sake of public good, this project emphasizes the importance of innovation and ethical deployments of newfound technologies such as machine learning advancements. And this creates a moral consideration in the precedent of future research by creating a long-lasting impact on technology innovation while maintaining or improving social welfare. And that will be it for today. Thank you guys so much for letting me present to you guys.